Right. As long as we are talking about energy and the work energy theorem, we spend a little bit of time talking about the idea of power and how that fits into the story. Tools like the work energy theorem allow us to calculate how much energy is transferred to an object or from an object by the interaction of forces between objects. The work doesn't tell us anything about how quickly that energy is transferred. If we want to quantify the rate that energy is transferred, then we need to think about power, because that's what power is. Average power is going to be the work divided by the time interval that that work is accomplished in. Power, therefore, is in MKS measured in joules per second, because work is measured in joules and time is measured in seconds. And that joule per second is called a watt. This is one of the nice places in a physics course where you actually have a connection between something in everyday life and something in physics. So unfortunately, a lot of our everyday life terminology is caught centuries in the past and is no longer useful, but we still use it because we don't change quickly. But when you see a 60-watt light bulb, that is this very same watt. That 60-watt light bulb is going to consume energy at a rate of 60 joules every second. A 1200-watt hair dryer is 1.2 kilojoules every second of energy to operate it. So unlike miles per hour, or um, you know, you have something that weighs 80 pounds, and there's a mismatch between the units that we measure things in for everyday life. This is precisely the same unit of measure for power in everyday life as we have in a physics course that's MKS based. All right, so that's the average power. At any instant in time, the instantaneous power is the derivative of the work with respect to time. And there is a handy relationship that relates power to the rate the work is done by a force. You take a force dot product with the velocity of an object, and that gives you the power, the rate that that force is doing work on the object, which is a nice connection between the sorts of forces you would have in a free body diagram and the rate that work is being done by those forces. All right, I'm going to try a question practicing these ideas. We have a sports car that could accelerate from 0 to 30 miles per hour in 1.5 seconds. How long does it take for it to accelerate from 0 to 60 miles per hour? And then the wording is important, assuming that the power of the engine is independent of velocity and neglect friction. Okay. So given that information can go from 0 to 30 in 1.5 seconds, how long is it going to take that same car to go 0 to 60? The power of the engine is independent of velocity. We get to ignore non-ideal effects like friction. So think about what you think the answer is, and then talk it over with your physics friends. All right, so why is it 6 seconds? So I wanted to back up a little bit and talk about the meaning about assuming that the power of the engine is independent of velocity. So power is equal to force dotted into the velocity. So the relationship between the force, the velocity of an object, and the rate that work is being done. So we're told that the power is independent of velocity, but from this equation, it's got velocity on the right-hand side. So for power to be independent of velocity, the force has to be decreasing as the velocity increases to keep the power constant. So you could think of different ways of thinking about how an engine is going to work. In this case, we're talking about the power being constant. You could also think that like the force it provides is constant. If that's the case, if the force is constant, then as the velocity increases, the power has to also ramp up to increase as well. Okay. Here we have a constant power. So as the object goes faster, the sports car goes faster, the force is diminished. All right. So then how do we get to 6 seconds out of this? So there's going to be a certain amount of work done to go from 0 to 30 in 1.5 seconds. To go from 0 to 60, my final speed is my final speed is twice as fast. So the kinetic energy that the car has is 4 times bigger than the work energy equation. That means that the final kinetic energy is 4 times bigger. That means the work done has to be 4 times bigger, but the power is constant. Okay. So to get 4 times more energy transferred to the car from the engine, it's going to take 4 times longer if the power is constant, and 4 times 1.5 seconds is 6 seconds. There you go.